So the next speaker will be Professor Ibrahim Börç-Misirlioglu from Sabancı University. He is also a theoretician, and he will talk. Yeah, I need the glasses. But anyway, Börç, please start the talk. Yeah.
So I hope everyone can hear me well.
Yeah, we hear you.
Okay, good. Well, so thank you, Lucian, for the introduction. I'm not a theoretician, in fact. I mean, I have happened to know some real theoreticians who work with pen and a paper only. So I'm more on the computational side of finding some solutions to some set of equations. But in the meantime, of course, I did learn a lot while interacting with such people. So I would like to thank the organizers for giving us the opportunity to present some of our results. And in fact, what I'm going to be discussing now will hopefully be somewhat stimulating given the previous discussions, because the same type of physics will also appear. So these are the collaborators who mostly are related to the first part of my talk, which is the phenomenological analysis of phase transitions under elastic clamping. So I'll also go over the details of the effect of boundary conditions. And so I will make a very general introduction. So when, in a ferroelectric, we have, I mean, depends on what view you take, you can see it as a structural phase transition, or you can also take it as some electrical order appearing in the sample. So we have the symmetrical phase, which when reaching a critical temperature deforms and then goes into what can be called the polar phase, and then it comes with some strain, and then we actually have these structural variants produced. So we are if we classify it as something similar to a first order transition, I try to sketch here, in fact, not an exactly first order transition, but like a weak first order transition, let me say. And then this reveals itself traditionally in the XRD. So we have usually, in especially bulk samples, we have these peak splittings, and people can actually characterize this. And then the variants, which could be both electrical and elastic, reveal themselves in the diffraction contrast mode in the TM. So this is a well-established topic, but there are a couple of questions here. So there are some fundamental questions. One of the things is that when you go to a thin film, the general perception is that the transition becomes second order. So you have the transition occurring from the symmetrical state to the non-symmetrical state, where the polarization locally, even microscopically, starts evolving from a very small number, like near zero value, and then gradually evolves. So, and much of the literature takes this point and then assumes these homogeneous transitions. And the first order transition, we all know the order parameter appears abruptly. And if we look at this Landau potential, so the original Landau wrote the potential only for the p square and p4 terms. It was a very simple formulation, which actually indicates that you go from a minima of this quadratic function to this fourth power function, and you pass some intermediate state where you have an infinite number of possible solutions. So when passing this state, so you, in fact, your polarization starts going from zero, and you gradually advance your, at some low temperature. So you have your system indicated by the blue balls here. So your high symmetry system, indicated by this red ball, rolls into one of these minima. And what is different in the first order transition? So it's a modification to the Landau potential by later contributions, including, I think, Devonshire, that this sixth term, when you add it, in fact, at the transition, you get this green potential where you have the equivalence of the energy. So that's why for the first order transition, your symmetrical phase and your low symmetric phases can actually coexist. So one of the things that we questioned with Professor Levanyuk and Nico was, is this, which one is feasible? And if we look at literature, we have, apart from the homogeneous transition approximation, which was, I think, famous paper of Partsev in 1998. After that, he also looked into the inhomogeneous states, which we can call the polydomain states. And our concern was if it is the case that the C phase transits to the paraelectric state through a second order transition, so how do we explain the thermodynamics of this? So in one of the papers, we were able to spot, using the same formulation, but with a slightly different potential. So the potential in Partsev's papers are written for stress. So we write it in strain because it's easier to, in fact, control and measure strain. Because strain, for instance, you can provide the misfit strain, which is a fixed number, and then it becomes easier to deal with the potential. So when we checked that for a film, we saw that the bulk modulus, so it is one of the elastic constants, that it can go to negative before reaching the critical temperature here. So, and this is, of course, not a possibility. You cannot have a negative bulk modulus. So this is something that that motivated us to question whether a film on a substrate can, in fact, undergo a homogeneous transition. So the first thing that we suspected was if we can have some phase coexistence in this region rather than a homogeneous transition. And so perovskite ferroelectric films are the best examples. So we're talking about a weak transition, a weak first order transition. And so this is, again, I hope you can see the pointer on your screen. So this is what has been discussed in Partsev. So we questioned the validity of this assumption. And then there's this paper in the 70s by Reutbert, where he did consider strong first order transitions and then found out that two-phase states can exist. But again, the same approach cannot be applied to weak first order transitions, because in a weak first order transition, you're close to the tri-critical point. So you're somewhere between a second order and a first order transition. So you still have this jump in the order parameter at the transition. And at the same time, Landau has shown that the bulk modulus or other elastic constants are strongly impacted by the if you define your system as a weak first order transition. So that's what we did. We took the Landau, like, well, this is something that we emphasize because so this is kind of like a modified Landau potential. So that's why I'll call it Landau. Like, now imagine a elastically clamped structure. And so you have, again, the high symmetric phase, and then you reach the critical temperature, Tc. And if you're in free state, then you go from the high symmetric to the low symmetric phase. And then what happens if you take the same system and clamp it? When you pass through the critical transition, well, of course, if the entire structure transforms, so you're going to have a huge cost of elastic energy, the elastically accumulated energy in your system. So that's why it is probably possible to, for not this case, we're going to show it for 1D, but this is probably intuitively understandable that the entire system will not want to transform, and you're going to have some portion of your system transforming. And what happens, again, what might happen intuitively on a substrate, if you go through the critical temperature, and you might expect to have, due to the clamping of the substrate, expect to have some regions of low symmetry and high symmetry phases coexist, again, due to the cost of the elastic energy. Because if the entire film transforms into the low symmetric phase, then this has a big cost of the elastic energy. Now, this has been analyzed earlier, so it wasn't us who talked about this for the first time. So the first, I think, serious attempt was in 2007 by Onuki and Minami, where they simulated the phase coexistence, starting from an Ising model, but adapting it to some type of a Gisbert-Landau type formulation. And moreover, the group of Selev also looked into this. They observed these coexistence of the tetragonal and monoclinic phases, which have different, degrees of symmetry, coexisting in vanadium oxide when it is in the form of when it was clamped from the sides, and then they came up with a phase diagram where they were looking at the metal and insulator and mixed states, mixed meaning the phase coexisting, the state that corresponds to phase coexistence as a function of elastic coupling. And so, so this is the difference. We're talking about, due to the elastic clamping, that the high symmetry phase might be elastically favored to exist deep into the region, where otherwise the low symmetry phase is stable. And this is quite different than, the phase coexistence that you have in traditional thermodynamics of phase transitions, where at the transition temperature, you have the equivalence of the energies of the phases. So the clamping indeed generates some interesting effects, can generate some interesting effects on the phase transitions. And this was our or the way we tried to explain the results of Onikima and Minami, that, well, I don't know if they were aware of it, but the bulk modulus of the system can actually enter a negative region. So you might actually have some region of phase coexistence rather than, having a negative bulk modulus, which is, again, like I said, impossible. So this is the point that we question, that a second order transition in a film proceeds homogeneously. And it turns out that a first order transition proceeding by phase coexistence is energetically more favorable. The first attempt that we had was looking at a 1D problem. And questioning, citing some of the results of Pertsev, for instance, in his phase diagrams, whether this paraelectric to C phase, the paraelectric to tetragonal transition, can actually proceed homogeneously or via second order manner. And we did compute the energy. So I'm going to actually show you some formulations on this, but then we find that the phase coexistence, which is this green curve, occurs. This is the energy versus the alpha is it's the first coefficient of the square of the of the order parameter. So we don't have any polarization here. So we don't also consider any electrostatic effects, just looking at elasticity. And we were able to find that the phase coexistence curve corresponds to lower energies, which means that when you're coming from a high temperature like this, so the green curve is the first curve that you're going to actually meet. So what this means is that a second order transition always occurs when this alpha value is at 0. But that means if you have phase coexistence, then you can actually intersect the phase coexistence curve, which indicates a first order transition, but proceeding inhomogeneously, meaning you have regions of this low symmetry phase. So you meet this curve earlier. That means your transition will probably happen way before the temperature at which the second order transition occurs. But of course, once you are in phase coexistence, then you actually proceed with that until some point, which is not clear here, but then the two intersect, and then eventually you have switching to the homogeneous state. Now, this was the system we analyzed. So we just took a one-dimensional system, wrote the potential, and we also wrote the piecewise energy of the two-phase state. So we did not consider any gradient energy. So we first excluded the interphase boundary energy between the low symmetry and the high symmetry phases. I don't want to go to the details of this, but then we assume the tricritical transition, so which meant that the fourth power term is almost zero, and so this allowed us to actually really work with the tricritical condition. And so I would like to show you the results. Well, okay, that was the piecewise formulation, because I'm going to be having a comparison. So we also did consider the effects of gradient, so which is indicated by this gradient term here, which comes from the equation of minimization. And we did a comparison. So why we first started with the case when we did not have any gradients, well, that applies to very large systems. So if you have a very large system, then you really don't worry about the interface boundary. But if you have finite systems, then you, of course, need to worry about the gradient energy between the low symmetry and the high symmetry phases. So we took the equations of minimization and continuity, which is a one-dimensional stress equation, in fact, and found that, that such a form has a solution already published by Falk in the 80s, and then this is kind of like the form. So we can take one of these curves, for instance, as a profile for the solution of eta when you're transiting from the low symmetry region to the high symmetry region. And the details are already published this year. And so on top of that, we applied numerics because, again, I don't want to go to the details. So this method had some approximations for progress. And then we also took the numerics approach at the same time. And we again wrote the displacement and eta boundary conditions. So the displacements are clamped at the end. So this is V is displacement. So we fix the rod at the end. And then we have neutral order parameter, meaning the surface has no privilege over the bulk when it comes to the transition characteristics. And so what we did basically was we solved the profile of eta both analytically and numerically, and then plugged the solutions into the I'm going back to the here to this equation, and then plotted results so that we could compare the energies and see if a homogeneous state is more favorable or an inhomogeneous state. And so these are the profiles that we obtained by taking the solution of Falk as reference. And of course, when you have a finite system, one interface is more favorable than two interfaces. So this turns out to be a metastable state. And what we did was we remained within this length, because the numerics could also give us metastable solutions, and then because we are interested in thermodynamic comparison, so we mostly stayed within these dimensions. And so this is the two-phase state without, I think this is for a sufficiently large system. So we have the two-phase state without the gradient, and then we have the two-phase state with the gradient. So I mean, the curves are quite close, overlapping, and this is the green one is the single homogeneous phase for this one-dimensional problem. And so again, like I said, we see that if you're coming from a high temperature, the first curve that you're going to be intersecting will be the two-phase state. And why I give the numerics of heating and cooling, because we could also check with the overheating and the undercooling behavior of these systems. And from that, we were able to generate the function of system size, like I said, all the way up to 125 nanometers, the high symmetry phase region, and then the two-phase region, and then we have the low symmetry phase region. So we have such a phase diagram. And the blue dashed line, dashed points are for the analytical solution, and the dark lines are for the numerics. And then we are also able to see how the order parameter, the average of the order parameter, in fact, scales at the transition with the length of the system. So the difference here is that once you have a finite system, you're gonna, some of the earlier works were assuming that you almost start from a zero fraction, but because of the interface energy, you have to start from a finite region of this low symmetry, and this is what we are trying to show here. So, and below some specific dimension, there's no way that you can have the low symmetry stability. And the problem with metastability I show here for this one-dimensional system, if you have like multiple interfaces, so we actually have these curves which are the metastability curves. So if you come from above and you have one interface, like this case, for instance, then this is your phase transition. But let's say if you have a large system with several interfaces, that this is going to be the curve that you're going to be intersecting, which means there will be a few degrees of difference in the phase transition. So this was the first part that we analyzed in a one-dimensional simple case the phenomenon of phase coexistence, assuming a weak first-order transition. And in finite systems, we have to account for the gradient on interface boundaries, because they do determine whether you will be able to observe a phase transition or not, depending on your system size. And especially for small systems, these boundaries are costly. So then the transition is pushed further to lower temperatures. And so we can have metastable states like with multiple interfaces. We did make the thermodynamic comparison over the single interface case. And we also have some other details, such as there are some other solutions that we found, but I'm not going to go into details of this. This is still something that we are discussing as a group. So following the one-dimensional case, well, we already had started working on the 2D system, but some discussions with Professor Levanyuk, I mean, he was more eager to publish the 1D results in a more detailed manner, citing that it's a simpler system. But then during that time, we already had the two-dimensional systems under focus. So we again have this film on a substrate when you're above the transition temperatures. So you're conforming to the substrate nicely, and then but when you have the first order transition, of course, the film wants to change its volume and then gets into a strained state, which is compensated by such formations of wavy profiles of eta, where you have regions of almost zero eta and then regions where you have maximal eta. And this, of course, is a function of film thickness. So we were able to also get the strain maps. And so this solution we got way before when you're cooling a system. So this is what you run into before you meet the second order transition temperature, which is the case of alpha equals 0, alpha being the coefficient, the lambda coefficient of the p squared term in the lambda potential. So and this is by the way isotropic case. So it was kind of like an academic case that we analyzed. But then what I did, I took this step a bit further. And well, okay, I show you here before I go to my recent results. I would like to show you how the transition temperature could depend on film thickness for various degrees of elastic coupling, and how the order parameter evolves as you heat it up. So these are for numbers of barium titanate. Barium titanate, we assume that the first order transition of barium titanate is close to 140 degrees Celsius. So and we have the order parameter disappearing gradually, but still those regions where the low symmetry phase exists has quite strong finite polarization, and if you hit this more, then they will disappear relatively abruptly. And this is a wide range of temperatures that this transition can occur. In the meantime, such a behavior could also give you a smearing effect, which is what people take as evidence for a second order transition. So, and yes, this is, again, I bring this in several times. So this is somewhere here. This is what corresponds to if you take the phase diagram of PATSEP. So this is the region that we have been questioning, that this cannot be a second order transition. Now, uh, one thing that I got interested in was the effect of electrostatic boundary condition on polydomain formation. I mean, I did not really know if there was some detailed systematic work on this, but one paper that I could find was from 2002 from the group of Longking Chan, and they have looked into two extreme cases, one with the short circuit and the other one with a vacuum on top and the bottom of a slab. And then they claimed that depending on the type of boundary condition, the electrical boundary condition you pick, you can have very different domain states, including elastic domains. So this was the paper that I ran into while I was looking into the effect of electrodes. And this is the formulation of that problem. So I did construct a two-dimensional system like this. So we have the metal behaving as ideal metal. We have the ferroelectric, which I took as 2080 PZT. We can imagine a semiconductor bottom electrode. At times, I will replace this with another ideal electrode, but this is for the sake of generality. And now we have the substrate, so we can apply potential from the top and then see how the order parameter, which is polarization now, evolves. So we have a two-dimensional system with the potential here. It's the Landau-like potential. We need to deal with elasticity for the system, and we also have the electrostatics that fulfill this Poisson equation. And the elasticity is just the continuity of the elastic fields, which has to be solved everywhere in the system except the metal. And then in case of semiconductor, we need to also define if you take it as an N-type semiconductor, so you have the carriers and then you have the ionized donors. So depending on the doping level, we introduce our numbers into here and then find what these are, which are then fed back here. So it's an iterative process. And I did this numerically. With the first solutions I provide are for the ideal electrode case. And so we have some slight misfit, and we found that the inhomogeneous states are favored. So we do get these elastic domains. So this is the out-of-plane polarization. So these green regions that you see are in-plane polarization regions. We can map the strains, and we can just change the misfit. And then, of course, as you go towards more relaxed misfit, then we might actually have more of these in-plane domains, which are the blue regions here. And again, look at the strains. And we can also turn the electrostatics off and see what happens. And what happens is just that those sharp boundaries kind of tend to get more diffuse and lousy because they don't need to worry about the abrupt changes in polarization that will cause the internal electric fields, which is also the case for this particular misfit. And well, if we again go back to the electrostatics, and if we turn the electrostatics on, so such systems, of course, will generate such potential gradients from which the internal electric fields can be computed and might aid in probably the effect of domain boundaries in, for instance, carrier transport. Now, if I go to semiconductor electrodes, well, we always end up with polydomain states. So we can understand that you can have up polarization and down polarization, but at the same time, we also get these elastic domains. By the way, these triangular domains are what we call the closure domains, which occur as transition from one domain to the other. But then we also have these elastic domains, which tend to depend on the substrate, the semiconductor. So this is telling you the doping level of semiconductor. So this is kind of almost metallic. But still, the finite screening effects at the interface still triggers the polydomain, the electrical domains especially. And as you go lower in the dopant concentrations, well, you start getting finer domains. And this is something that we are familiar with from many other works. But we also have these elastic domain regions appearing. The same story for the misfit that is lower than this 1% compression. So if we go to 0.5%, then we have, because of the tetragonality, so an arrangement of in-plane and out-of-plane domains appears to be relaxing the system better. And even when you have the substrate as a moderately doped semiconductor, then we kind of have even the out-of-plane regions disappear. And we think, I mean, this is at least what I think, that elastic domains are helping with also the reduction of the depolarizing fields. So this is maybe how we can explain how the elastic domains are disappearing. And one way to look at this, of course, is to compare energies. So we can get the solutions and feed them into the energy expression and then check with the energy. So this is the, for a semiconductor electrode, and in fact, this is almost metallic-like, we see that the pole domain state is always stable relative to the single domain states, which is shown by the red curve here. And if I assume ideal electrodes, because the finite screening immediately kills the single domain state, which has been a focus of many works, especially in early 2000. So if I replace the bottom electrode, the bottom semiconductor electrode, with an ideal bottom electrode, then what I see is that the single domain state gets to be stabilized. But still the polydomain version, the polydomain state appears as more stable. And if I check the individual terms of the single domain state, I see that the electrostatic energy of the system is quite minimal. Well, we have some elastic energy here. This is the cubic state elastic energy. And in fact, well, when we are doing a thermodynamic comparison, if we take this as a reference, so this has to be displaced to 0. Well, this curve will go down a bit more, but that still doesn't change the story. So the polydomain state appears to be more stable. And the reason why we have almost no electrostatic energy cost to the system is because the system is able to adjust its polarization to minimize that energy. And if I also compare with the fixed misfit state. So here, for instance, I don't allow the system to undergo any type of relaxation. So the misfit is fixed, which is close to what has been published in earlier phase diagrams. So we do get a difference. And if you have the electrostatic, so this is what pushes the system here. But like I said, when the system has this electrostatic cost, it tries to get into a state of, so I have, I think maybe 5 more minutes. So the system actually goes to a higher energy, but then the reason for this is, despite the fact that it tries to minimize the electrostatic energy, is because, okay, well, that is something I'm going to explain in the next slide, but there's, I just skipped this hump here. So if we look at the case with this elasticity, so I think this is a good example to cite to show the onset of phase coexistence. While doing these solutions, what I noticed is that if I just exclude electrostatics and just look at the system from an elasticity point of view and the regular lambda terms, so we can have such situations where the single domain state just evolves, and at some point it starts lowering its energy. And this, I noticed, is kind of like a phase coexistence, starting off a phase coexistence. If you heat this further, so at different temperatures, so we see that the polar phase or the low symmetry phase disappears very gradually. But it's also still first order, because these regions, if you can look at the scale, still remain sustain an ordered parameter that is close to the one that corresponds to the energy minima. Now, okay, coming back to this discussion again, this electrostatic situation in the single domain. What we noticed is that as you try to minimize the electrostatic energy, that means you're deviating from your local polarization minima. So that's why despite the fact that you minimize electrostatic energy, then you have you're at a polarization value that's far away from the minima, which raises the energy of the system. So these terms have more positive values relative to the polydomain state, which apparently can minimize electrostatic energy more effectively. And then this deviation, in fact, causes your phase transition temperatures to go up. So I just plotted here the ferroelectric part of the energy, and then the comparison actually shows that these terms plotted here show the difference between what happens for a polydomain and a single domain state. And if we apply electric field, so I said we can apply bias to the system, and we cannot get rid of the elastic domain, so they remain for the case of ideal electrodes, and also in the case of semiconductor bottom electrode for almost like a metallic, like a highly doped semiconductor. We still see that portion of the domains remain. And again, the elastic domains are still there. So we cannot move them much. Now, I talked about the melting of the polydomain state. I think this is towards the end of my talk. And so it was an interesting case to look at from these numerical experiments. And I did check the electrostatics on and electrostatics off case. So if you have the electrostatics on for a polydomain state going towards the phase transition, you again have these paraelectric regions forming and some polar regions, but then you have diffuse boundary, and the reason is because abrupt rotations of polarization will cost you electrostatic energy from the Poisson equation. And at some temperature, probably this is like really at the transition temperature. So you have these regions, but still a first order like transition, and then they disappear eventually. And what happens with if you turn the electrostatics off for the same system, well, you have such type of a transition which also can reach higher temperatures. And this is the effect of the electrostatic fields on the transition and the phase coexistence. These results are not published yet, so this is still work under progress. What happens on a multi-domain, polydomain state when you're in a semiconductor electrode? So this is just the amplitude map of polarization. So all the polarization components are here. Again, we see an identical behavior, but of course at much lower temperatures if you check with the previous one because of the bottom semiconductor. And again, we have this very gradual disappearance, but still regions that remain in their polarization states close to the minima rather than going gradually to zero. So these regions then will just disappear abruptly. Well, these are my some of the remarks. So I did talk about the effect of elasticity. So we did question the second order transition assumption, and then we have shown that the phase transition can proceed by the nucleation of the second phase before the critical temperature. When I say critical temperature, I'm talking about second order temperature here. Which, by the way, this phase coexistence can still reveal itself like a second order transition, and I've shown that the polydomain state appears to be favored over single domain states. This is still something that I'm questioning, and this is ongoing work. And but one thing is that the electrostatics definitely have an impact on formation of A domains. So A domains cannot be thought of only to minimize elastic energy. And there's also this phenomenon of melting of the polydomain state, which again is still under scrutiny. So thank you very much for your valuable time. I hope I was able to finish.
Thank you, Bert. Now, maybe we have time for one short question. Please.
Hi, Porsche. Love your talk. I have a question regarding the gradient term. In your models and in most people's models, I always see the gradient energy as the square of the gradient, and that's quite natural. And that's the energy of the gradient itself. What I never see considered is the coupling of the gradient to the polarization, i.e. flexoelectricity. Is it because numerically it's much smaller, or is it difficult to treat it analytically, or?
Well, yeah, okay. So there are, I think, both operational difficulties, and but at the same time, we try to stay somewhat loyal to the original form of this potential. So I hope you can see the screen where we have the gradients of
No,
this.
we can only see your face at the moment.
Oh, okay.
Here. Yeah, okay.
Sorry,
All right.
sorry, sorry.
Now we see it. Yeah.
Huh. Yeah, okay. So so we have these. In fact, that is also something that we have been questioning. I mean, are these additional terms, this flexoelectric effect related terms that are introduced into this potential as a relatively unnatural term, or can they be derived naturally from the presence of this potential? So that, so I don't have a clear answer to your question, but regarding the use of this potential and not having the flexoelectric effect, that is probably my best argument, that we are just trying to stick with the fundamental terms for the system that was reported.
But you have no idea of whether quantitatively the pure gradient term and the gradient coupling terms are of very different size, because if they were comparable in magnitude, then this is just wrong. You should consider both.
Yeah, definitely. Yeah. So in fact, yeah, to be objective, before making any comments, one has to compare the magnitudes.
Fair enough. Okay.
So it's a conceptual. Looks like a conceptual difficulty, but still, I think there's more to it than what I say.
Okay. Thank you.
Okay, thank you, Borch.
You're welcome.
Thank you again.